Look inside an untreated industrial pipeline, and you will see a silent mechanical failure in progress. The dissolved minerals carried in the untreated water stream rapidly crystallize, completely choking off the flow from the inside out. The primary culprits behind this scale buildup are calcium and magnesium ions, a combination operators simply call hardness. When raw water hits high temperatures or extreme pressures, these specific ions fall out of solution. They instantly stick to the hottest, most critical surfaces in your plant, like forced circulation heat exchangers and main circulation pipelines. Ignore this chemistry, and the resulting scale creates a thermal barrier. Your plant will burn more energy to hit the same temperatures, right up until the equipment physically clogs and shuts down your entire operation. Selecting a pre-treatment strategy requires navigating the technical difference between removing specific scaling minerals and stripping the water of its entire mineral load. First, you have to measure total dissolved solids, or TDS. This is the sum total of every single salt and mineral dissolved in your water supply. As this diagram shows, hardness is merely a small fraction of that overall TDS. Calcium and magnesium are just two specific components living inside a much larger mix of dissolved elements. Because of this, effectively removing hardness to stop scaling does not automatically reduce the overall TDS footprint. The water is soft, but it is still full of other dissolved salts. Your choice of treatment strategy hinges entirely on this distinction. You must determine if your downstream equipment requires water with zero scale-causing minerals or water with zero solids whatsoever. If your goal is strictly to prevent scale, ion exchange softening is the baseline technique used in most industrial plants. The physical setup is straightforward. Hard water is pumped through a pressurized vessel packed with a deep bed of cation exchange resin. Inside the bed, a chemical swap occurs. Calcium and magnesium become trapped in the resin, while harmless sodium is pushed into the stream. The trade-off is strictly numerical. As the chart demonstrates, hardness drops to zero, but the overall TDS level remains exactly the same. This process creates an operational burden. Once the resin beads are saturated with calcium, they are flushed with a heavy brine solution that requires a recurring budget for salt and generates a secondary wastewater stream. Ion exchange provides highly cost-effective protection against scale, but if your process demands high purity, low salt water, this method falls completely short. When simple resin softening isn't enough, plants turn to the brute force purification of reverse osmosis, or RO. RO systems rely on massive high-pressure pumps to force the heavy feed water through incredibly fine, tightly woven semi-permeable membranes. The pores are so tight that they reject almost everything. RO strips out the hardness, but it also removes up to 99% of all total dissolved solids, yielding ultra-pure permeate. That extreme purity comes with heavy penalties. RO systems demand massive amounts of electricity to maintain pressure, and if any hardness sneaks into the feed water, the membrane itself will scale and tear. To protect the RO, or to achieve partial purification, operators use nanofiltration as a strategic middle ground. Comparing the two side by side, nanofiltration operates at a much lower pressure. It strongly rejects the large, multivalent hardness ions, but allows smaller, monovalent ions, like sodium, to slip through the pores. Membrane technologies give you unparalleled control over water purity, but they require high capital investment and flawless pretreatment. Otherwise, the industrial environment will destroy them. Some plants pump in raw water that is so heavily scaled and contaminated that delicate membranes or resin beds would fail on day one. In those severe scenarios, plants rely on chemical precipitation, specifically lime soda ash softening, for heavy-duty bulk treatment. Operators dose the raw water with calcium hydroxide and sodium carbonate. This triggers a massive reaction, forcing the invisible, dissolved hardness ions to physically convert into heavy, solid precipitates. It is highly effective at pulling out severe hardness and high silica. The drawback is the physical waste. The process generates massive volumes of heady sludge at the bottom of the clarifiers, requiring constant mechanical extraction and disposal. Chemical precipitation provides the bulk stabilization necessary to protect sensitive downstream equipment from severe incoming raw water. There is an alternative strategy for extreme environments. You can control the behavior of the hardness without actually removing it from the water. This is achieved through continuous anti-scalant polymer dosing. Instead of extracting the minerals, specific polymers are injected into the stream. These chemicals wrap around the surface of growing calcium and magnesium crystals. This barrier prevents the crystals from fusing together or sticking to the equipment walls. This becomes the primary defense in evaporators and zero liquid discharge systems. As water is boiled away, the remaining minerals concentrate until they hit their saturation limit. These polymers keep those minerals suspended in the fluid even when they would normally solidify. Anti-scalants allow plants to achieve extreme water recovery rates. But it is a high-risk game. The minerals are still in the water, suspended by a chemical thread. If the dosing pump fails, catastrophic scale forms almost instantly. Understanding the chemistry only matters if you can apply it. The final step is mapping the right technological trade-off to your specific plant equipment. You have 3 operational levers to pull: physically remove all solids, selectively swap the scale-causing ions, or chemically suspend the threat in the flow. This decision matrix breaks down exactly how to match your equipment's sensitivities to the correct method. For basic boiler makeup and low-pressure cooling towers, you only need to stop scaling. Assign ion exchange for cost-effective hardness removal, since overall TDS reduction isn't strictly required. When feeding high-volume raw water clarifiers, assign lime soda ash precipitation to knock down extreme bulk contaminants before reaching sensitive systems. For zero liquid discharge plants requiring extreme purity, deploy reverse osmosis to strip out the overall TDS, protected by an upstream nanofiltration stage. And when pushing evaporators to their absolute thermal limits, utilize anti-scalant dosing to keep the hyper-concentrated minerals safely suspended in the reject stream. An effective industrial softening strategy balances your equipment's specific tolerance for dissolved solids against the capital and operational costs of the treatment.